Dear student, in our earlier video, we have studied pressure of an ideal gas. In the present video, we'll be studying laws of equipartition of energy and degrees of freedom. We have studied earlier that the average kinetic energy of a single molecule is equal to 3 by 2 kb into T. All molecules are in random motion with no specific direction, so the total energy is divided equally for all the three translational directions, that is x, y and z. So the mean energy associated with every component of translational kinetic energy will be equal to half kb into T. Let us try to understand this equipartition of energy in a simple way. Consider a container in which we have placed a large number of ping pong balls. Now suppose we throw some energy randomly into our box. Now these ping pong balls will start moving. Now what do you expect? Do you expect that the figure A, where all the ping pong balls are moving in one direction, will be the possible result, or the one which is showed in figure B? Yes, your guess is right. We expect figure B, in which all the ping pong balls are moving in random motion. That is the possible result, where all the ping pong balls are moving in a random direction. So the total energy is evenly distributed in all possible directions, which makes these balls move in all possible directions. The total number of coordinates or independent quantities required to describe the position and configuration of the system completely is what we call it as degrees of freedom. Now in the diagram, we have shown a diatomic molecule. Now it will have a rotational motion possible, as well as it will have a translational motion, and it might have a vibrational motion also. Now in the animation, you can clearly see the molecule can have 3 translational motion as well as 2 rotational motion. Now there might be possibility of a vibrational motion also. Now let us derive Mayer's relation. Consider 1 mole of a ideal gas enclosed in a cylinder with a tight frictionless airtight piston. Let P, V and T be pressure, volume and temperature of the gas. Suppose the gas is heated by keeping volume constant. As you see in the animation, the temperature as well as pressure increases. So the total energy, the amount of heat supplied, dQ1, will be used to increase the internal energy. Now that is given by CV into dt, where this CV is molar specific heat at constant volume. Now suppose the gas is now heated at constant pressure. The part of energy will be used to do external work, and the remaining is used to increase the internal energy. As you see in the animation, the piston moves in the upward direction, as well as the temperature also increases. So this dQ2, the energy which is supplied, will be equal to Cp into dT, where Cp is molar specific heat at constant pressure. Now the total energy which is supplied will be used in two ways as stated earlier. One, to increase the internal energy, and to do the external work. So what we get is Cp minus Cv into dt, which is equal to P into dV. Now using ideal gas equation which we have written, P into dV, which is equal to R into dt. So we can have Cp minus Cv, which is equal to R. Now here specific heat is in a unit of calories and the work is done in the unit of joules. So to make it in a single unit, we divide it by a constant J, which is mechanical equivalent of heat. So we get equation Cp minus Cv, which is equal to R divided by J. For monoatomic gas molecule, only translational motion is possible. So the average kinetic energy per atom, as we have studied, is 3 by 2 kb into T. For 1 mole of a gas, it will be 3 by 2 Na kb into T, where Na is Avogadro's number. Now molar specific heat at constant volume, that is Cv, is nothing but dE upon dt. So we get that equal to 3 by 2 into R. Now substituting this Cv in Mayer's relation, which we have derived earlier, we get molar specific heat at constant pressure will be 5 by 2 into R. Now if I take the ratio of molar specific heat at constant pressure to molar specific heat at constant volume, will be equal to 5 divided by 3, which is equal to 1.66. Now for diatomic molecule with rigid rotor, that means there is no vibrational component possible. You will have 3 translational degrees of freedom and 2 rotational degrees of freedom. Now each component has got energy value equal to half kb into T. So total average kinetic energy will be equal to 5 by 2 Na kb into T. Now molar specific heat at constant volume, that is Cv, will be equal to dE upon dt, which will be equal to 5 by 2 into R. Now again substituting this into Mayer's relation, we get molar specific heat at constant pressure as 7 by 2 into R. Now if I take the ratio of molar specific heat at constant pressure to molar specific heat at constant volume, it comes as 7 by 5, which is equal to 1.4. Now for a diatomic molecule with non-rigid rotator, that means it will have a components of vibrational motion also. So the molecules will have 3 translational degrees of freedom, 2 rotational degrees of freedom, and additionally 2 more vibrational degrees of freedom. So the total average kinetic energy will be equal to sum of all these 3 components, which gives equal to 7 by 2 Na Kb into T. Now molar specific heat at constant volume Cv will be nothing but dE upon dt, which gives equal to 7 by 2 into R. Now if I substitute this into Mayer's relation, the molar specific heat at constant pressure is given by 9 by 2 into R. Now if I take the ratio of molar specific heat at constant pressure to molar specific heat at constant volume, I get equal to 9 divided by 7. Now for polyatomic molecule, that means it has got molecules more than 2, will have 3 degrees of translational degrees of freedom. You will have 3 rotational degrees of freedom, which are about their mutual perpendicular axis, and f degrees of vibrational motion. So the resultant average kinetic energy will be sum of all these components, from where we get molar specific heat at constant volume as 3 plus F into R. Now again substituting this into Mayer's relation, we get molar specific heat at constant pressure as 4 plus F into R. Now if I take the ratio of molar specific heat at constant pressure to molar specific heat at constant volume, it comes as 4 plus F divided by 3 plus F.